This is a pre-class video on unsymmetrical fault analysis. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE. In this video, I will be explaining open conductor fault and a brief review on different faults like LG fault, LL fault and double line to ground fault. This is session 3. In the first session 1 and session 2, I explained introduction about unsymmetrical faults and finding the fault current and sequence network for line to ground fault, line to line fault, double line to ground fault with and without fault impedance. So, let us see the unsymmetrical fault on power system with fault impedance. Here I considered 3 transmission lines and 3 stubs is considered A, B, C, and this is unloaded transmission line. Since it is unloaded, the currents which are flowing in the B and C, that is IB is 0 and IC value will be 0. And here the fault current is your IA, that is it is grounded through impedance, and this value will be I is equal to IA is the fault current. Therefore, the value of VA is IA into ZF. These are the terminal conditions for a single line to ground fault with fault impedance. So, to derive the solution, what we do is, let us consider the symmetrical component of currents. As we know that the symmetrical component of currents are IA0, IA1, IA2. This is given by 1/3 of 1 1 1 1 A square 1 A square A, and here we have IA, IB and IC. Here IB is 0 and IC is also 0 and IA. So, here we can get IA0 as 1/3 of IA. Similarly, you can get this is equal to IA1 is equal to IA2. That means here currents are equal. Currents are equal means all the 3 sequence networks are connected in series. So, this means IA is your fault current, that is 3 times of IA0. From this relation you can write. So, after this finding, let us consider the sequence networks of the generator. From the sequence network of the generator, we can write the voltage equation, that is VA0, VA1, VA2 as 0, this is pre-fault voltage 0 minus Z0, Z1, Z2, 0, 0, 0, 0, 0, and then IA0, IA1 and IA2. So, if you simplify these further, this gives IA0 is equal to IA1 is equal to IA2. So, if you substitute this here and simplify further, you will get VA0 is equal to minus Z0 into IA1 and VA1 is pre-fault voltage minus IA1 into Z1. Similarly, VA2 is minus Z2 into IA1. When we add this, because it is required to find VA is equal to IF into ZF, therefore, VA is nothing but the phase voltage. It is the sum of symmetrical component of voltages VA0, VA1, VA2. Here we have the expression for VA0, VA1 and VA2. Substitute here, you will get the expression for after simplifying you will get the expression for IA1. IA1 will be VPF divided by Z0 plus Z1 plus Z2 plus 3 times of ZF. So, this is how we can find the IA1 value. Once you know the IA1 value, you can easily find the fault current, because the fault current expression is 3 times of IA0 or it is 3 times of IA1. If you know the IA1 expression, substitute here, you will get the value. So, that is what here it is written IA1, then the fault current is nothing but the IA is IF, that is 3 times of IA1. So, here 3 times of the fault current expression is 3 times of VPF divided by Z0 plus Z2 plus Z0 plus 3 times of ZF. So, here positive, negative and zero sequence networks, they are connected in series and they are connected in series with the fault impedance. Next, let us consider the line to line fault. Here also we have considered the line A, line B and line C. The line A is unloaded, therefore, the fault current here is 0, and here IB and IC is shorted, therefore, IB is equal to minus IC and this is equal to your fault current, and here you can write the expression for voltages. VB minus VC is nothing but ZF into IB, ZF into IB, then VC is nothing but VB minus ZF into IB. The symmetrical components of currents, after substituting IA is equal to 0 and IB and IC. So, you have the expression for the symmetrical component of currents. So, let us use the same formula IA0, IA1, IA2, that is equal to 1/3 of 1 A square 1 A square A, it is 0 IB minus IB. So, if you simplify this, then you will get IA0 is 0 and IA1 is minus IA2. If you multiply the matrices, you will get this. That means, in a line to line fault, in a sequence network, we do not have the zero sequence network, we have only the positive and negative sequence network, they are connected in parallel. So, similarly, the sequence component of voltages and currents, you can have the relation, that is IA, IB and IC are the unbalanced currents. So, we can write this unbalanced current in terms of the symmetrical components, that is IA0 is 0, IA1, IA2 is minus IA1, here 1 A square A 1 A square. So, if you simplify this for IB, because IB is the fault current. So, in the next slide I will tell the expression for the IB. So, IB is minus j root 3 IA1 if you multiply the previous matrix. So, here IA1 is nothing but root 3, IA1 is VF divided by Z1 plus Z2 plus ZF. This is the IB, this is the fault current. So, the expression fault current is found, and positive and negative sequence networks connected in parallel, and it is connected in series with the fault impedance. As per this equation, it is written. So, after this, let us understand double line to ground fault with fault impedance. As we discussed already this in detail, here also we have considered the same B and C phases as faulty phase. Here B and C are shorted and it is grounded through the fault impedance, and the terminal conditions easily you can write. So, here IA is 0 because no load is connected to that, no current flows. Here IB and IC, they are added to give the fault current. Here this Vb is equal to Vc is equal to Zf into If, or it can be written as Zf into Ib plus Ic. Our aim is to get the expression for this Vb, Vc, and then we have to get the expression for Ib plus Ic. Then we have to write the equivalent circuit of sequence network and the fault current expression. So, it is proved from the previous session derivation that here positive, negative and zero sequence networks are connected in parallel, and here between positive zero negative sequence and zero sequence we have ZF. So, you can get the expression for IA0. 3 times of IA0 will be the fault current. So, IA0 will be this. So, this is how one can find the sequence network for double into ground fault with fault impedance. So, next let us consider the 3-phase fault. 3-phase fault. Here 3-phase fault means fault happened in all the 3 phases. Here phase A, phase B, phase C, all the 3 phases get shorted, and they have shorted with fault impedance. If that is the case, then how to write the sequence network? This sequence network is having only the positive sequence, just like we have explained in the previous. So, here BA1 is VF minus ZA1 IA1 into Z1, this is IA1 ZF. Here IA1 is E, that is pre-fault voltage divided by Z1 plus ZF. So, this is very simple to analyze. On per phase basis we can do the calculations. Open conductor fault. Open conductor fault is in series with the line. The line currents and series voltages between broken ends of the conductors are required to be determined. So, here I considered the open conductor fault specifications. Here phase A is open, phase B is open, phase C is open. Because of the fault, here the terminals are A dash, B dash and C dash, and the sequence network you can write like this. Here these are the 2 terminals. So, here fault FF dash, and the voltage here is VAA dash. Suppose conductor A gets open, AA dash becomes because of the fault, and the currents you can write like this, IA1. So, this is the analysis of open conductor fault, how to write the sequence network for this. And let us consider this phase voltages. Phase voltages, how to write the phase voltages? See here, this is the phase voltages. We have 3 phases, IA, IB, IC, and the phase currents. Suppose if you take one line and if it is open, okay, then the terminals A dash becomes, then the voltage will be wave A dash. Similarly, B phase opens, then the phase voltage is B dash, and C phase open means this. And symmetrical component of currents are IA0, IA1, IA2, and symmetrical component of voltages. And this is the one parameter, that is phase voltage. Its positive sequence, negative sequence and zero sequence voltages you can mark like this. So, this is very important for next derivation. And the sequence network, for positive sequence, negative sequence and zero sequence you can write like this. So, same, but parameters are different. Here positive sequence, negative sequence, zero sequence, and IA1, IA2 and IA0. So, almost it is same. Next we will understand how to write the two conductors open. Here also two conductors are open, here B and C conductors are open. If two conductors are open, the terminal conditions are VA dash is 0. Why? Because it is not shorted, no? Therefore 0. Then VB dash comes and VCC dash comes. Here IB is 0 because it is open, and here IC value will be 0. These are the terminal conditions. IB and IC are zeros and VA dash is 0. So symmetrical component of voltages, if you consider VA dash, symmetrical components are what? So that is 1 positive sequence, negative sequence and 0 sequence. The sum will be equal to 0 because VA dash is 0. Similarly, the currents IA0 is equal to IA1 is equal to IA0, that is equal to IA divided by 3. Why? Because here IA0 is nothing but 1/3 of IA plus IB plus IC. So if this is the case, then IB and IC are zeros, then IA0 will be 1/3. If you write the other two symmetrical component relations IA1 and IA2, so that will be also can be written. So let us see here, once the currents are same means they are connected in series. Once the currents are same, here as you see the currents are same, voltages positive, negative and 0 sequence voltages are added, means they are connected in series. See here, positive sequence component, positive sequence network, negative sequence network and 0 sequence network. Now they are all connected in series. See here, it is connected in series, it is connected in series. It is easy to mark the terminals, that is this is positive sequence component VA1, negative sequence and 0 sequence. So FF dash IA1, IA2 and IA0. Like this you can write the positive, negative and 0 sequence values. So with this, suppose if you consider one conductor fault in the same lines, you can analyze. So here one conductor fault if you consider, then here B and C phases are not opened, therefore VBB dash is 0 and VCC dash is 0, and the current which is flowing in this is 0, IA is 0. So if you write the symmetrical component of voltages like VAA naught dash, that is given by 1/3 of VAA dash plus VBB dash plus VCC dash, then if you write the final answer, these are zeros, therefore it is 1/3 of VAA dash. So here similarly you can calculate BAA Similarly, you can calculate VAA dash 1 and VAA dash 2. This is 0 sequence, positive sequence and negative sequence values. The answer will be same. VAA dash 1/3 of VAA dash. The same lines you can derive. So we come to know that these voltages are same, means the positive, negative and 0 sequence networks are connected in parallel. So that you can see in the next slide. Here positive sequence network, here you can see positive sequence network, negative sequence network and 0 sequence, they are connected in parallel, because see VAA dash 1 that is equal to VAA dash 2 that is equal to VAA dash naught. So they are connected in parallel. So with this I will be ending this video.